All right, this is page 21 of our notes. So just now we're looking at actually doing the calculations and how we do them. So part one, we have to get the balanced reaction, okay, which is part one of all stoichiometric calculations. Okay, again, for redox reactions, we have to balance them a little different. Okay, we always start by listing all the entities present to find out what our possible oxidizing and reducing agents are. Then we want to find our strongest oxidizing agent, okay, and write down its reduction half reaction exactly as we see it in our data booklet. Okay, and then we find our strongest reducing agent, and then we have to write down its oxidation half reaction. So if we're taking it from our data booklet, we have to flip it and have the backwards reaction. Next, we have to balance number of electrons lost and gained by multiplying one or both equations by a number. Add the two balance half reaction equations to obtain a net ionic equation. We'll do an example of how to do this if you forgot. Okay, and then predict whether the net ionic equation represents a spontaneous or non-spontaneous redox reaction. Okay, so we always want to say whether it's spontaneous or not, if it's going to happen. Okay, and then once we have that balanced reaction, we're actually going to do the stoichiometric calculation. So underneath the equation, we'll write the information that's given. Okay, what are we given a concentration, volumes, okay, and then what are we required to find? Usually, again, it's going to be looking at it'll be a solution stoich, and we'll be looking for concentrations. Okay, once we have that, we're going to calculate the number of moles of the known solution using C equals N over V. We'll rearrange that so N equals C times V. We also should know unit analysis, so when I do my example, I'll try and show you both ways. Okay, and then use the mole ratio from the known equation, or from the balanced equation, to determine the number of moles of unknown and calculate the concentration. Okay, then once we have our N, divided by our volume to get our new concentration. Okay, meniscus reading we aren't going to worry too much about, just because we aren't going to actually be doing the lab. Okay, some learning tips. Okay, for stoich, again, we always need balance reaction. Okay, with measurements and conversion factors. Okay, convert given measurements into chemical amounts, then calculate the amount of moles using the mole ratio, and convert into its final concentration or whatever you're looking for. Okay, so the example we'll use, okay, is on page 22 of our notes. And we'll do this as an example. So of analyzing for tin. Okay, so we're kind of given a write-up here talking about where we'd use this. So extensive long-term research was found that treating children's teeth with fluoride significantly reduces tooth decay. When this was first discovered, toothpaste was produced containing tin 2 fluoride. And then we're going to look at analysis of the report. So basically, we're going to look at this lab is used the stoichiometric method in a redox chemical analysis to find out the concentration of tin 2 ions in the solution that's prepared for the research of the toothpaste. Okay, so we're given our table. Again, all titrations kind of give us a table of something like this. Okay, and so we're looking for the amount concentration of tin 2 ions in a solution prepared for the research of this toothpaste. Okay, so we're given, so the first thing we want to do, write down what we have. So we have tin 2 ions. Okay, that's something we're going to be looking for. We have KMnO4, potassium permanganate, so we have K plus. We have MnO4 minus. It uses acidic tin 2, so again, as soon as you see the acidic, we can add our H plus ions. And then because they're aqueous, we always have H2O. So now we look at our table of half reactions on page 7. Okay, to find out oxidizing agents and reducing agents. Again, these are our strongest oxidizing agents starting at the top and going down. These are our strongest reducing agents starting at the bottom and going up. Okay, and so label them. So we got tin 2, okay, is a reducing agent. Okay, we we got potassium as oxidizing agent. MnO4 and H plus is a strong oxidizing agent. H plus on its own is an oxidizing agent. Water can be both a reducing agent and an oxidizing agent. Tin can also be an oxidizing agent. I forgot to add that over here. Okay, so now we've labeled it all, so that's kind of our step two, or that's still in part of step one of balancing the reaction. Now we have to find our strongest oxidizing agent, strongest reducing agent. So we're just looking what's closest to the top is our strongest oxidizing agent, so right there. What's closest to the bottom for reducing agent, so tin 2 is our reducing agent. Okay, now we write out our half reaction. We have our strongest oxidizing agent, exactly like we see it here. So that's our oxidizing agent half reaction or reduction reaction. Again, our oxidation reaction is going to be our tin 2 plus. And that's going to produce tin 4 plus. So we're just doing the reverse of this reaction, plus 2 electrons. Now we need to balance out our electrons. So we're going to times this by 5, times this by 2, and we'll write our net ionic equation down here. Okay, so we have our total. This is now our balance equation. I took out the electrons because we had 10 on each side, so they cancel each other out. Okay, now we want to write down what we're given. Okay, so if we look up here, so we have a titration of 10 milliliters of acidified tin 2. So under tin 2, we have a volume, we have 10.00 milliliters. Okay, and then we have a concentration of our MnO4, 0.0832 moles per liter. To find the volume, okay, we have our difference in readings between 1 and 2. We're given the final volume. Here is our 3 final volumes. Okay, we need to find the average of these 3 is going to give us this volume here. So again, 12.4, 12.3, and 12.5. So it's really easy to find the average. It's right in the middle. You can add them up and divide them by 3, but in this case, yeah, it's just as simple as that middle number. And then what we're looking for is the concentration of tin 2. Okay, so that's this is what we're given, this is what we're required to find. Now we can do our calculations. So again, if we were using our formulas, we would use our C equals N over V to solve for N and then go on. I'm going to do it by unit analysis. So we always start with kind of something that, like, this would be a conversion factor to moles over liters. So we're going to start with something that's not a conversion factor. We'll start with our volume in milliliters. So we have 12.4 milliliters. Again, because this is in milliliters, I know they'll cancel out. If you ever aren't sure, convert them to liters, and that'll always be right. And so now we're going to times that by our concentration, 0.832 moles per liter. So our liters cancel with liters. So right now, again, if I put an equal sign, I'd have how many millimoles of MnO4. And now I'm going to times it by, I want to know how many moles of tin 2 I have. So I'm going to times it by required over given. So 5 moles, so our mole ratio over 2 moles. And then, so our moles cancel out here. I want to get our moles cancel, or I want to have moles over liters. So I'm going to have 1 over 10 milliliters. Okay, my milli cancels with this milli, so I'm left with moles over liters is my answer, and that's what I want. I should get 0.26. Actually, we need 3 significant digits, so it'd actually be 258 moles per liter. Okay, if I was doing it the longer way, okay, I'd start C equals N over V, so N is equal to C times V. I'd want to convert the V to liters, so I'd divide or times this by 1 liter is equal to 1,000 milliliters. So I have my concentration 0.0832 moles per liter times 0.0124 liters. Get my N 0.00103 moles, times that by my mole ratio. I'm in another room here. Okay. So then I get my moles of given is equal to of required. This would be moles of given. Moles are required 0.010, this should be 5/2. Wrote down wrong. And then I should get 0.0025792 moles of my required, and then final C equals N over V. So we get our number of moles 0.0025792 divided by our concentration in liters, and we still get the same number, 0.258 moles per liter.